At the heart of 19th century physics stood a profound uncertainty about the true nature of electricity and magnetism. Scientists could observe sparks, currents, and compass needles deflecting near wires, yet the deeper question remained unresolved. What exactly produced magnetism? Was it something special about electric currents flowing through metal conductors, or was magnetism a more fundamental consequence of electric charge simply being in motion? The first keynote centers on the decisive moment when this question was answered through Henry Rowland's rotating disk experiment, which provided the first direct experimental proof that moving electric charge itself creates a magnetic field. This confirmation was not merely a technical achievement. It reshaped the conceptual foundations of physics. To understand why Rowland's proof mattered so deeply, it is necessary to step into the intellectual climate of the time. By the mid-1800s, electricity and magnetism were already known to be connected. Ørsted had shown that a current carrying wire could deflect a compass needle, and Ampere had developed mathematical laws describing magnetic forces between currents. These discoveries revealed a relationship, but they did not fully explain its nature. An electric current was understood as something flowing through a conductor, but what was actually moving remained unclear. Some physicists imagined electricity as a fluid, others as opposing fluids, and still others as stresses within matter itself. Because currents were always observed inside wires, it was tempting to believe that the conductor played a special role in creating magnetism. At the same time, James Clerk Maxwell had introduced a revolutionary theoretical framework. His equations described electricity and magnetism as parts of a single electromagnetic field, predicting that electric charges in motion should produce magnetic effects regardless of how that motion occurred. According to this view, magnetism was not tied to wires, but to motion itself. However, theory alone was not enough. Many physicists remained skeptical, arguing that mathematical elegance could not substitute for direct experimental evidence. What was needed was a clear demonstration that electric charge, when set into motion without forming a conventional current in a wire, could still generate magnetism. Henry Augustus Rowland approached this challenge with both technical skill and conceptual clarity. He recognized that if one could move electric charge in a controlled way, independent of metallic conduction, it would be possible to isolate motion as the decisive factor. His solution was remarkably simple in principle. He used a disk made of insulating material, coated it with electric charge, and then rotated it at high speed. As the disk spun, the electric charges on its surface moved in circular paths. If Maxwell's ideas were correct, this circulating charge should behave like a current loop and produce a magnetic field. What made the experiment difficult was not the idea, but the execution. The magnetic effects predicted were extremely weak, far weaker than those produced by ordinary currents in wires. Detecting them required instruments of exceptional sensitivity and careful shielding from external disturbances. Rowland designed his setup with meticulous attention to detail. He placed sensitive magnetic needles and detection devices near the rotating disk, ensuring that any observed effect could only be attributed to the motion of the charged surface. When the experiment was finally performed, the results were subtle but unmistakable. As the disk began to rotate, the magnetic detectors showed a measurable deflection. When the rotation stopped, the magnetic effect disappeared. When the direction of rotation was reversed, the direction of the magnetic field reversed as well. These observations matched theoretical predictions precisely. There was no conductor carrying a current in the traditional sense, no wire guiding electrons from one place to another. There was only electric charge in motion, and yet magnetism appeared exactly as Maxwell's theory said it should. This moment marked a turning point in physics. For the first time, magnetism had been directly linked to the motion of electric charge itself, independent of material pathways. The experiment demonstrated that a current is not a special phenomenon confined to wires, but simply a convenient example of moving charge. The conductor does not create magnetism. It merely allows charge to move in an organized way. This realization stripped magnetism of much of its mystery and placed it firmly within a unified electromagnetic framework. The importance of this proof extended far beyond the immediate experiment. It provided powerful experimental support for Maxwell's equations at a time when they were still being debated and tested. Maxwell's theory predicted not only magnetic fields from moving charges, but also electromagnetic waves traveling through space at the speed of light. By confirming one of the key assumptions underlying the theory, Rowland's work strengthened confidence in the entire electromagnetic world. It helped convince the scientific community that electricity and magnetism were not separate forces awkwardly linked by coincidence, but different expressions of a single underlying reality. Rowland's result also influenced how physicists thought about matter itself. If magnetism arises from moving charge, then magnetic properties of materials must ultimately come from motions of charged particles within atoms. Although the electron had not yet been discovered, this idea pointed directly toward a microscopic explanation of magnetism. Later, when electrons were identified as fundamental carriers of electric charge, Rowland's experiment gained even greater significance. It became clear that magnetic fields produced by currents in wires, by spinning disks, and by atomic electrons all shared the same origin: charge in motion. The experiment also clarified the role of relativity in electromagnetism, even though relativity itself had not yet been formulated. Later physicists realized that electric and magnetic fields transform into one another depending on the observer's frame of reference. What appears as a purely electric field in one frame can appear as a combination of electric and magnetic fields in another. Rowland's demonstration that motion alone generates magnetism fit naturally into this deeper understanding. Magnetism could be seen as an effect of electric forces viewed from a moving perspective, an idea that would later become central to Einstein's theory of special relativity. Beyond theory, the proof had practical implications that would unfold over decades. Once magnetism was understood as a consequence of moving charge, engineers could design machines with greater confidence and precision. Electric motors, generators, and transformers all rely on controlled motion of charge and the magnetic fields that result. Although these technologies were already developing, a clearer theoretical foundation accelerated innovation and refinement. The rotating disk, humble in appearance, contributed to the intellectual infrastructure that made modern electrical engineering possible. What is especially striking about Rowland's work is how it exemplifies the power of experimental simplicity. The apparatus was not enormous, nor was it technologically extravagant. Its strength lay in isolating a single idea and testing it directly. By removing the wire and retaining only motion, Rowland eliminated alternative explanations. This clarity is what gave the experiment its persuasive force. It was not just that magnetism appeared, but that it appeared exactly when and how motion demanded it should. In the broader narrative of science, this achievement illustrates how progress often depends on resolving subtle conceptual questions. Before Rowland, physicists already knew many practical facts about electricity and magnetism. They could build devices and make predictions. Yet something essential was missing: certainty about the underlying cause. The rotating disk provided that certainty. It transformed an assumption into an observed fact and closed a debate that had lingered for years. The first keynote, the proof that moving electric charge creates a magnetic field, is therefore more than a historical detail. It represents a moment when nature's behavior aligned perfectly with human reasoning, when theory and experiment met without contradiction. From that point onward, electromagnetism could be understood as a unified phenomenon governed by universal laws, applicable from laboratory instruments to cosmic scales. In confirming that magnetism is born from motion, Rowland's rotating disk did not merely change physics. It clarified the language in which physics describes reality itself. During the 19th century, physics was not only a collection of experiments and equations, but also a field shaped by disagreement, skepticism, and competing interpretations of nature. One of the most persistent debates of the era concerned the true source of magnetism. While it was known that electric currents in wires could generate magnetic fields, there was no agreement on whether this effect arose from the motion of electricity itself or from some special interaction between electricity and the material of the conductor. The second keynote focuses on how Rowland's rotating disk experiment decisively settled this debate by showing that electricity in motion behaves as a current, regardless of the presence of a wire, and that magnetism is a universal consequence of moving charge. At the center of the controversy was the definition of an electric current. Today, it is taken for granted that a current is simply a flow of electric charge, but in the 19th century, this idea was far from obvious. Electricity was often treated as an abstract entity whose behavior depended strongly on the medium through which it passed. Wires, electrolytes, and insulating materials were thought to interact with electricity in fundamentally different ways. Because magnetism had only been observed in connection with currents in conductors, it was reasonable to suspect that the conductor itself played a crucial role in producing magnetic effects. Some physicists proposed that magnetism emerged from microscopic processes inside metals, perhaps involving the alignment of molecular currents or special interactions between electricity and matter. Others believed that electric currents involved unique forces that did not apply to static or freely moving charges. These views allowed for the possibility that electricity moving outside a conductor or moving as a static distribution on an insulating surface might not produce magnetism at all. The absence of decisive experiments kept the debate alive, and theoretical arguments alone could not settle it. Rowland recognized that the disagreement could only be resolved by separating electricity from the conductor and observing whether magnetism still appeared. His rotating disk provided exactly this separation. By charging an insulating disk and setting it into rotation, he created a situation in which electric charge moved in a controlled and measurable way, but without flowing through a wire. This design stripped the problem down to its essentials. If magnetism appeared, it would mean that the conductor was not the source of the effect. If it did not, the traditional view would gain support. The importance of this approach cannot be overstated. Scientific debates often persist because experiments fail to isolate the critical variable. In this case, the critical variable was motion itself. By eliminating the wire, Rowland removed the most common source of confusion. What remained was a direct test of whether motion of charge, by itself, could produce magnetic effects. When the experiment was conducted, the outcome was clear and consistent. As the charged disk rotated, magnetic detectors registered a field whose strength and direction depended on the speed and direction of rotation. These changes followed the same rules that governed ordinary electric currents. When the disk spun faster, the magnetic effect increased. When the disk's rotation reversed, the magnetic field reversed. When the disk stopped, the magnetic field vanished. The behavior was indistinguishable from that of a current loop, even though no current flowed through a conductor. This result struck at the heart of the debate. It demonstrated that electricity in motion behaves as a current, regardless of the medium in which it moves. The conductor was revealed to be incidental, not fundamental. Its role was to guide and sustain the motion of charge, not to create magnetism. The defining feature of a current was motion, not material context. This conclusion simplified and unified the understanding of electromagnetism in a way that earlier theories had failed to do. By settling this question, Rowland's work helped resolve inconsistencies that had troubled physicists for decades. If magnetism had depended on special properties of conductors, then different materials should have produced fundamentally different magnetic effects under similar conditions. While some variations were observed, the underlying laws remained the same across materials. Rowland's experiment explained this consistency. Since magnetism arises from motion of charge, and charge behaves universally, the same magnetic laws apply everywhere. Differences between materials could be understood as differences in how easily charge moves, not differences in the nature of magnetism itself. The implications of this resolution extended beyond electromagnetism. It reinforced a broader philosophical shift in physics away from materials, specific explanations, and toward universal principles. Instead of asking how electricity behaves in copper versus glass, physicists could focus on how electric charge behaves in motion, independent of the substance involved. This shift laid the groundwork for later developments in theoretical physics, where particles and fields replaced materials as the primary objects of study. The experiment also influenced how scientists interpreted earlier results. Phenomena such as magnetization, induction, and electromagnetic forces could now be re-examined with a clearer understanding of their cause. Induced currents, for example, could be seen as the result of changing motion of charge in response to varying magnetic fields, rather than mysterious effects tied to specific materials. This perspective unified a wide range of observations under a single conceptual framework. Rowland's resolution of the debate also strengthened the status of experimental physics as the ultimate arbiter of truth. Theoretical arguments on both sides of the controversy had been sophisticated and persuasive, yet they led to conflicting conclusions. It was only through careful experimentation that the issue could be settled. This reinforced the idea that physical theories must ultimately answer to observation, no matter how elegant or intuitive they may seem. The clarity provided by the rotating disk experiment also helped bridge the gap between classical physics and emerging ideas about the microscopic world. Although atoms and electrons were not yet fully understood, the notion that electricity consisted of discrete charges in motion began to gain traction. If moving charge produced magnetism, then the magnetic properties of matter could be traced back to motions of charges at the atomic level. This insight would later prove essential in the development of atomic theory and solid-state physics. In retrospect, it is striking how much confusion rested on a single unresolved assumption. Once it was shown that electricity in motion behaves as a current regardless of context, many puzzles simply dissolved. The debate that had once seemed complex and deeply philosophical turned out to hinge on a straightforward physical fact. Rowland's rotating disk did not introduce a new force or phenomenon. It clarified the nature of an existing one. The resolution of this debate also influenced scientific education and communication. Textbooks could now define electric current in a more precise and general way. Students could be taught that magnetism is a consequence of moving charge, not a special property of wires or metals. This clarity made electromagnetism more accessible and conceptually coherent, helping to train a new generation of physicists and engineers. Ultimately, the second keynote highlights how Rowland's experiment transformed disagreement into understanding. By proving that electricity in motion behaves universally as a current, the rotating disk removed a major conceptual barrier in physics. It replaced speculation with evidence and replaced fragmented explanations with a unified principle. In doing so, it not only settled a 19th century debate but also shaped the intellectual structure of modern electromagnetic theory, ensuring that future discoveries would rest on a firm and unambiguous foundation. In the history of science, some experiments do more than confirm a prediction. They change the level of confidence with which an entire theory is accepted. The third keynote centers on this kind of transformation. Henry Rowland's rotating disk experiment did not merely demonstrate a curious magnetic effect. It provided crucial experimental reinforcement for James Clerk Maxwell's electromagnetic theory at a time when that theory, though mathematically powerful, was still viewed by many as abstract and uncertain. By showing that moving electric charge generates magnetism exactly as Maxwell's equations implied, Rowland's work helped unify electricity and magnetism into a single, coherent physical framework and moved physics decisively toward a field-based understanding of nature. Before Maxwell, electricity and magnetism were linked through empirical laws, but they remained conceptually fragmented. Coulomb's law described electric forces between charges, while separate laws governed magnets and currents. These laws worked well in their own domains, yet they lacked a unifying vision. Maxwell changed this by introducing a set of equations that treated electric and magnetic fields as interconnected aspects of one electromagnetic field. His equations implied that changing electric fields could create magnetic fields, that changing magnetic fields could create electric fields, and that electromagnetic disturbances could propagate through space as waves. This was a profound shift, but it came at a cost. The mathematics was complex, and many of the predicted effects were subtle and difficult to test experimentally. Among the assumptions embedded in Maxwell's framework was the idea that magnetism arises from the motion of electric charge. In this view, an electric current was simply a macroscopic manifestation of moving charges, and magnetic fields were the natural consequence of that motion. While this idea fit neatly into the equations, it lacked direct experimental confirmation outside the familiar case of currents in wires. Critics argued that Maxwell's theory, elegant as it was, relied too heavily on unverified assumptions. They wanted experiments that could isolate these assumptions and test them directly. Rowland's rotating disk addressed this need with remarkable precision. By demonstrating that a charged insulating disk, when set into rotation, produced a magnetic field, the experiment directly validated one of Maxwell's core ideas. The magnetic field observed around the spinning disk was not an incidental effect or a special case. It followed the same quantitative rules as magnetic fields produced by ordinary currents. This agreement between theory and experiment strengthened the credibility of Maxwell's equations in a way that purely mathematical arguments could not. The timing of this confirmation was critical. Maxwell's theory was competing with alternative conceptual models that attempted to explain electromagnetic phenomena without invoking fields as fundamental entities. Some physicists preferred action, at a distance explanations, where forces acted directly between charges without the mediation of fields. Others viewed fields as convenient mathematical tools rather than physical realities. Rowland's experiment lent support to the field concept by showing that magnetism emerged naturally from the motion of charge, consistent with a continuous electromagnetic field filling space. This reinforcement of field theory had far-reaching consequences. Once fields were accepted as real physical entities, it became easier to understand how electromagnetic effects could propagate through empty space. This understanding was essential for the later experimental discovery of electromagnetic waves by Heinrich Hertz. Hertz's experiments showed that electromagnetic waves behaved exactly as Maxwell's equations predicted, traveling at the speed of light and exhibiting reflection, refraction, and interference. The confidence needed to pursue such experiments was built, in part, on earlier confirmations like Rowland's. Rowland's work also helped clarify the symmetry between electricity and magnetism that lay at the heart of Maxwell's theory. If moving charge produces magnetism, then magnetism is not a separate or secondary phenomenon, but an inevitable counterpart to electricity. This symmetry suggested that electric and magnetic fields were two perspectives on the same underlying reality. Such a view encouraged physicists to look for deeper unifications, not only within electromagnetism, but across all of physics. The experiment also contributed to a shift in how physical explanations were framed. Instead of focusing on forces between objects, physicists increasingly emphasized the behavior of fields in space and time. In the rotating disk experiment, nothing tangible passed between the disk and the magnetic detector, yet the detector responded. This response made sense if space itself was permeated by an electromagnetic field influenced by the motion of charge. The experiment thus reinforced the idea that fields, though invisible, have real physical effects. As Maxwell's theory gained acceptance, it began to influence other areas of physics. Thermodynamics, optics, and mechanics were re-examined in light of field concepts. The realization that light itself was an electromagnetic wave blurred the boundaries between disciplines that had once seemed distinct. Electricity, magnetism, and optics were no longer separate subjects, but parts of a unified whole. Rowland's confirmation of magnetic motion played a role in solidifying this synthesis. The strengthening of Maxwell's framework also had implications for how experiments were designed and interpreted. Physicists became more willing to trust theoretical predictions and to build experiments aimed at detecting subtle field effects. This trust did not replace skepticism, but it balanced it with a recognition that well-founded theory could guide discovery. The rotating disk experiment exemplified this productive interplay between theory and experiment. Maxwell's equations suggested a phenomenon, and Rowland's careful measurements brought it into the realm of observation. In the longer term, this unification set the stage for the next great revolutions in physics. Special relativity, developed by Albert Einstein, was deeply rooted in electromagnetic theory. Einstein's insight that the laws of physics, including those of electromagnetism, should be the same in all inertial frames, led him to rethink space and time themselves. Magnetism, in relativistic terms, could be understood as an electric effect viewed from a moving frame of reference. This interpretation makes sense only if magnetism truly arises from motion of charge, a fact that Rowland's experiment had already demonstrated. Quantum theory, too, inherited the unified electromagnetic framework that Maxwell and his experimental supporters had established. The quantum description of light as photons and of electromagnetic interactions as exchanges of quanta presupposed that electricity and magnetism were manifestations of a single interaction. Without the earlier consolidation of classical electromagnetism, the transition to quantum electrodynamics would have been far more difficult. It is also worth noting the cultural impact of this strengthening of theory. Maxwell's equations came to symbolize the power of mathematical physics, showing how abstract reasoning could reveal deep truths about nature. Experiments like Rowland's provided the necessary grounding, preventing theory from drifting into speculation. Together, they demonstrated a model of scientific progress in which mathematics and measurement advance hand in hand. The rotating disk experiment thus occupies a special place in the story of electromagnetism. It was not the most dramatic or widely known experiment of its time, yet its importance lay in how precisely it targeted a key theoretical assumption. By confirming that moving charge generates magnetism in exactly the way Maxwell's theory required, Rowland helped transform that theory from a bold proposal into a reliable foundation. In hindsight, it becomes clear that unification is one of the most powerful drivers of scientific understanding. When disparate phenomena are shown to arise from a common cause, the resulting theory is not only simpler but also more predictive. Rowland's work contributed to such unification by tying magnetism directly to electric motion, eliminating the need for separate explanations. This unification did not close the book on electromagnetism, but it provided a stable platform from which new questions could be asked. The third keynote, therefore, is not just about experimental confirmation. It is about trust. It is about the moment when physicists began to trust Maxwell's equations as a true description of reality, not merely a mathematical convenience. That trust reshaped research priorities, inspired new experiments, and guided theoretical exploration for decades to come. In reinforcing the unity of electricity and magnetism, Rowland's rotating disk helped turn a collection of phenomena into a coherent theory, and in doing so, it played a quiet yet decisive role in the emergence of modern physics. Long after the rotating disk stopped spinning in Henry Rowland's laboratory, its influence continued to move through science, technology, and the way humanity understands the physical world. The fourth keynote is not limited to the moment of discovery itself, but extends outward, tracing how a single experimental confirmation reshaped future physics and enabled technologies that define modern life. By revealing that magnetism is an inevitable result of moving electric charge, Rowland's work quietly became a cornerstone upon which vast areas of science and engineering were built. One of the most profound consequences of this insight was the clarification of cause and effect in electromagnetic phenomena. Once magnetism was understood as arising from motion of charge, engineers and physicists could design systems with far greater precision. Electric motors, for example, operate by forcing electric charges to move through coils, producing magnetic fields that interact with other fields to generate motion. While early motors existed before Rowland's experiment, their design was guided largely by trial and error. A deeper understanding of magnetic motion allowed for more efficient designs, improved materials, and reliable predictions of performance. The same principle applied to generators, which convert mechanical rotation into electric current by moving charges through magnetic fields. The conceptual clarity provided by Rowland's proof ensured that these devices were not just practical tools, but embodiments of fundamental physical laws. The influence of this understanding extended into the rapidly developing field of electrical power distribution. As cities began to rely on large-scale electrical networks, the behavior of currents and magnetic fields became a matter of public safety and economic importance. Transformers, which depend on changing magnetic fields produced by alternating currents, could be analyzed and optimized only with a firm grasp of how moving charge generates magnetism. The rotating disk experiment helped anchor this understanding in experimental reality, reinforcing confidence in the equations used to design complex power systems. Beyond engineering, Rowland's result shaped the direction of theoretical physics in subtle but lasting ways. Once magnetism was firmly linked to charge motion, it became natural to search for magnetic effects wherever charge moved, even at scales far smaller than any laboratory apparatus. This perspective guided early investigations into atomic structure. When electrons were discovered and identified as carriers of electric charge, their motion within atoms provided an immediate explanation for many magnetic properties of matter. Paramagnetism, diamagnetism, and ferromagnetism could all be traced back, in different ways, to the behavior of electrons in motion. The rotating disk, in this sense, anticipated the microscopic origins of magnetism long before they could be directly observed. The experiment also influenced how physicists thought about rotation and motion on cosmic scales. Planets, stars, and galaxies contain vast amounts of charged matter in motion. The realization that moving charge generates magnetic fields suggested that celestial bodies could possess magnetic fields due to their rotation and internal charge dynamics. This insight laid conceptual groundwork for later studies of planetary magnetospheres, solar magnetic activity, and cosmic magnetic fields. While these phenomena involve complexities far beyond Rowland's laboratory setup, the underlying principle remains the same. Magnetism, whether in a spinning disk or a rotating planet, emerges from motion. As physics entered the 20th century, the legacy of magnetic motion became even more apparent through the development of relativity. Einstein's theory revealed that electric and magnetic fields are not separate entities, but components of a single electromagnetic field that transform into one another depending on the observer's motion. This idea finds a natural precursor in Rowland's work. If magnetism arises from moving charge, then changes in perspective and motion must alter how electromagnetic phenomena appear. The rotating disk experiment, though classical in nature, aligns seamlessly with this relativistic understanding, showing that magnetism is deeply connected to motion at the most fundamental level. Quantum physics further extended the reach of this principle. In quantum electrodynamics, electromagnetic interactions are described in terms of fields and particles exchanging quanta. Yet, even in this abstract framework, the classical insight remains visible. Charged particles in motion interact through electromagnetic fields, producing forces and radiation. The continuity between Rowland's classical experiment and modern quantum theory highlights the enduring relevance of his result. It was not a narrow or temporary discovery, but one that fit naturally into every subsequent refinement of physical theory. The technological impact of this understanding is woven into everyday life. Magnetic storage devices, medical imaging technologies, and communication systems all rely, directly or indirectly, on controlled motion of electric charge and the magnetic fields it produces. Even the simple act of generating radio waves involves accelerating charges and harnessing the resulting electromagnetic fields. While these applications are far removed in complexity from a rotating disk, they share the same conceptual foundation. The proof that moving charge generates magnetism made it possible to treat these technologies as predictable and controllable, rather than mysterious or empirical. Equally important is the philosophical lesson embedded in this legacy. Rowland's experiment demonstrated how a clear answer to a fundamental question can unlock progress across multiple domains. Before his work, magnetism could be seen as an isolated phenomenon, tied to specific materials or special conditions. Afterward, it became part of a universal story about motion and charge. This shift exemplifies how science advances not only by discovering new phenomena, but by revealing deeper connections among known ones. The rotating disk also serves as a reminder of the power of modest experiments. It did not require unprecedented resources or massive infrastructure. Its success depended on careful reasoning, precise measurement, and a willingness to challenge assumptions. In an era when scientific progress is often associated with large collaborations and complex instruments, this historical example underscores the enduring value of conceptual clarity and experimental elegance. In education, the influence of this keynote persists in how electromagnetism is taught. Students learn that currents produce magnetic fields and that currents are flows of charge. This chain of reasoning, now presented as obvious, rests on experimental confirmations like Rowland's. By grounding abstract definitions in observable facts, the rotating disk helped shape a coherent pedagogical narrative that connects simple ideas to advanced theory. Looking back, it becomes clear that the rotating disk changed physics not by dramatic spectacle, but by quiet certainty. It closed a conceptual gap, strengthened a unifying theory, and provided a foundation for both technological innovation and theoretical exploration. The legacy of Rowland's proof of magnetic motion is visible wherever electricity is harnessed, wherever magnetic fields are measured, and wherever motion is understood as a source of physical influence. The fourth keynote, therefore, is a story of continuity. From a spinning disk in a 19th century laboratory to the vast networks of modern technology and the deep theories of contemporary physics, the same principle endures. Moving electric charge creates magnetism. This simple truth, once uncertain, now underlies much of what defines the modern world. In revealing it so clearly, Rowland's experiment ensured that a small rotation in understanding would lead to a lasting revolution in physics.